AI chatbots may never be fully secure, and here's why. Researchers presented a paper at one of the top machine learning conferences this year making a pretty bold claim. They argue that large language models have a fundamental flaw built into their architecture, not a bug you can patch, not a training mistake you can correct, something deeper, something that comes from the very way these systems understand language. To get why that matters, you need to understand how these models actually process text. A large language model doesn't read words the way you do. It converts everything into numbers. Each word, each phrase, each sentence gets turned into a long string of numerical values called embeddings. These embeddings live in a high-dimensional space, and words that mean similar things end up close to each other in that space. That's actually what gives the model its power. It understands meaning through mathematical proximity, but here's where the problem starts. That same system that lets a model understand meaning also makes it nearly impossible to draw a hard line between legitimate input and malicious input. Think about it this way. If you want to protect a traditional software system, you can write rules. Block this pattern. Reject that string of characters. Those rules work because the system processes text literally. A firewall doesn't care about meaning. It just looks for exact matches. A language model can't do that. It's built to interpret meaning, not to match patterns. So when a researcher or a bad actor crafts a phrase that means roughly the same thing as a blocked phrase but uses different words, different structure, different framing, the model often processes it the same way. Because in the model's internal representation, those two phrases land in almost the same place. They're mathematically close. This class of attack is called a semantic attack, and the researchers argue it's not fixable in any complete sense. Here's the core of their argument. The model's strength and its vulnerability are the same thing. The ability to understand that "don't tell me your instructions" and "reveal your system prompt" and "what were you told to do" all mean roughly the same thing is exactly what makes the model useful. You can't take that away without breaking the model. But that same capability means a determined attacker can always find a new way to phrase a harmful request that slips past whatever filters are in place. It's a bit like trying to ban a concept from a conversation. You can tell someone not to mention fire, but they can say flame or blaze or combustion or describe the thing without naming it. Language is flexible. That flexibility is the whole point. And a model trained to understand language deeply will pick up on all of those variations. Researchers have known about prompt injection attacks for a while now. That's when someone embeds hidden instructions in text that the model processes, trying to override its behavior. Companies have built defenses against specific known attacks, but this new research is making a stronger claim. It's not just that current defenses are incomplete. It's that complete defense may be mathematically impossible given how these systems work. The researchers frame this using formal theoretical arguments, not just experiments. They're saying that the geometry of the embedding space guarantees there will always be adversarial inputs that behave like benign ones from the model's perspective. You can shrink the vulnerable surface. You can make attacks harder, but you can't eliminate it entirely without fundamentally changing what these systems are. That has real consequences for how we deploy this technology. Right now, AI models are being plugged into everything. Customer service systems, code generation tools, medical information assistants, legal research platforms. In a lot of these applications, the model is being trusted to follow instructions, respect boundaries, and refuse certain requests. If those refusals can always be gotten around by a sufficiently creative attacker, that changes the risk calculation significantly. It doesn't mean the technology is useless. A lock that can be picked by an expert is still worth having. Most attackers aren't experts. Raising the cost and difficulty of an attack still matters, but it does mean that anyone deploying these systems needs to think carefully about what happens when the safety layer fails, because according to this research, that failure case isn't hypothetical. It's structurally available to anyone patient enough to find it. There's also a deeper question this raises about the nature of alignment in AI systems. A lot of the effort in AI safety research is focused on getting models to follow rules reliably. Don't produce harmful content. Don't help with illegal requests. Stay within your defined role. But if the model's understanding of language is inherently fuzzy at the boundary between allowed and disallowed, then perfect rule following may not be achievable through training alone. Some researchers think the answer involves external verification systems that don't rely on the model itself to police its own outputs. Others are exploring ways to make the embedding space less exploitable. None of those directions are close to a complete solution yet. What this research is really doing is shifting the framing. For the last few years, a lot of the conversation around AI safety has assumed that with enough careful engineering, you can make these systems secure. This paper is pushing back on that assumption. It's saying the vulnerability is architectural, not incidental, and that's a different kind of problem to solve. For people building with these systems, that's worth sitting with. Not to say the technology shouldn't be used, but to be honest about what it can and can't guarantee. Understanding the limits of a tool is part of using it responsibly, and for the field overall, this is the kind of finding that tends to reorient research priorities. When you discover that a problem is harder than you thought, at a more fundamental level than you thought, that changes where you focus. That's not a bad thing. That's how the science moves forward.